Inferential statistics involves forming conclusions about a population parameter. In previous videos, we learned how to conduct a hypothesis testing and how to build a confidence interval estimate of one population parameter. In this video, we will look at methods on how to compare two population parameters. And we will start with conducting a hypothesis testing about two population proportions and building a confidence interval estimate of the difference of two population proportions. In order to test a claim about two population proportions, three requirements must be met. First, the sample proportions are from two simple random samples. Second, the two samples are independent, meaning the sample values from one sample do not match or pair up somehow with the sample values from the other sample. And third requirement, for each of the two samples, there are at least 5 successes and at least 5 failures. That is, n times p hat is greater or equal 5 and n times q hat is greater or equal 5 for each of the two samples. We are going to look at the example on testing a claim about two population proportions using technology, StatCrunch. But just in case, if you want to calculate it by hand, the test statistic for two proportions can be found with the following formula. Z is equal the difference between sample proportions minus the difference between population proportions divided by the square root of p bar times q bar divided by n1, the total values in first sample, plus p bar times q bar divided by the total values in the second sample, where the difference between two population proportions assumed to be 0. This is our null hypothesis. And p bar is a pooled sample proportion that combines two samples proportions into one proportion and can be found by the formula x1 plus x2 divided by n1 plus n2. And q bar is equal 1 minus p bar. Now let's read the example. In the article, The Denomination Effect by Priya, Raghubir, and Joydeep Srivastava, Journal of Consumer Research, Volume 36, researchers reported results from studies conducted to determine whether people have different spending characteristics when they have larger bills, such as $20 bill, instead of smaller bills, such as $21 bills. In one of the trials that they conducted, 89 undergraduate business students from two different colleges were randomly assigned to two different groups. In the so-called dollar bill group, 46 subjects were given dollar bills. The quarter group consisted of 43 subjects given quarters. All subjects from both groups were given a choice of keeping the money or buying gum or mints. The article includes the claim that money in large denomination is less likely to be spent relative to an equivalent amount in many smaller denominations. Let's test that claim using a 0.05 significance level with the following sample data from the study. To help us organize the data, I created a table. Let's call first population Group 1, subjects who were given $1 bill, and population 2, Group 2, subjects who were given 4 quarters. X, the number of those who spent the money, and the total number in the group. In the first group, there were 12 people who spent the money out of 46 total. So let's find sample proportion of the first sample and sample proportion of the second sample. Remember, p hat is equal x over n. 12 over 46 is equal 0.26, and 27 over 43 is equal 0.63. We can see that the first sample proportion is smaller than the second sample proportion. Let's test if the difference is significant. Identify the claim. Money in a large denomination is less likely to be spent relative to an equivalent amount in many smaller denominations. So basically, those who are given larger bills are less likely to spend the money. So our claim is that P1 is less than P2. Therefore, the opposite claim will be P1 is greater or equal P2. Let's now write null and alternative hypothesis. Remember, null hypothesis is that there is no difference between two population proportions. P1 is equal to P2, or we can write it as P1 minus P2 is equal to 0. Alternative hypothesis will be our original claim because our original claim did not have an equal sign. P1 is less than P2. We're going to use significance level alpha 0.05 to test this claim. And we're going to test this claim using p-value and critical value method. And then we'll construct a confidence interval estimate of the difference between two population proportions. Let's draw a distribution. It's a normal distribution. If we were doing it manually, we would use table A2, and our critical value and test statistic will be z-score. Let's identify whether it's left tail test, right tail test, or two-tail test. We can identify that by looking at alternative hypothesis. Alternative hypothesis has less than sign. Therefore, our test is going to be left-tailed. And critical value and significant level are located on the left. 0.05 is on the left, and the critical value is going to be negative. We will first test the claim using p-value. So let's find the p-value. I'm going to use StatCrunch. To test the hypothesis about two population proportions in StatCrunch, go to Stat, Proportion Stats, Two Samples, and we have Summary. So we're going to test it with Summary. Enter the number of successes in the first sample, 12. Total number of observations, 46. The number of successes in the second sample, 27. Total number of observations, 43. Hypothesis test for P1 minus P2 equals 0. Alternative hypothesis, P1 is less than P2. Compute. P-value is 0.0002. Let's write it down. P-value significantly less than significance level of 0.05. Because p-value is less than significant level alpha, we reject the null hypothesis. Let's look at the table to help us toward final conclusion. We start answering the question, does the original claim contain the condition of equality? No. Do you reject null hypothesis? Yes, we rejected null hypothesis. We can say the sample data support the claim that our original claim was that P1 is less than P2. Now let's rewrite it in human language. We can say there is sufficient evidence to support the claim that people with money in large denominations are less likely to spend relative to people with an equivalent amount of money in smaller denominations. Now let's test this claim using the critical value method. We will need to find the critical value, or the z-score, that corresponds to 0.05 area on the left of the z-score. Let's use StatCrunch. From previous calculations, we already know that the z-statistic is negative 3.49, rounded to 2 decimals. We need to compare it with the critical value. To find critical value, go to Stat, Calculators, Normal, adjust the direction of distribution. We have left tail test, so it's going to be to the left. Area to the left is 0.05. Compute. The critical value is negative 1.645. Let's write it down. Negative 1.645. And the z-statistic is the z-score that separates p-value on the left of that z-score. And it's equal to, from StatCrunch, negative 3.49. The z-statistic is in the critical region, If the z-statistic is in the critical region, we reject the null hypothesis. If the test statistic is in non-critical region, if it was somewhere here, we would fail to reject null hypothesis. Conclusion is going to be the same. There is sufficient evidence to support the claim that people with money in large denominations are less likely to spend relative to people with an equivalent amount of money in smaller denominations. So if you don't want to spend a lot of money, keep it in large denomination bills. And now we're going to test the same claim using the confidence interval method. Let's build the confidence interval. Because our test is left tail test, we need to add the right tail the same amount, 0.05 on the right. That will make our confidence interval 1 minus 0.05 plus 0.05 is 0.1. 1 minus 0.1 is equal 0.9. So our confidence interval is 90% or 0.9. Let's use StatCrunch. To build a confidence interval for two population proportions in StatCrunch, go to Stat, Proportion Stats, Choose Sample with Summary, enter the same values, number of successes in the first sample, 12, total number of observations, 46, number of successes in the second sample, 27, and total number of observations in the second sample, 43. Choose the confidence interval for the difference between two population proportions, adjust the level to 90% or 0.9, compute. The confidence interval limits are negative 0.528, rounded to 3 decimals, to negative 0.206. Let's write it down. The interval limits, I'm going to write it right here because I'm running out of space a little bit, are negative 0.528 to negative 0.206. As you can see, the confidence interval limits do not include 0. 0 would be way on the right, and here are the confidence interval limits. The values of the difference between two population proportions are not the same. In fact, if the difference between two population proportions is negative, P1 minus P2 is less than 0, that means that P2 is greater than P1. So there does appear to be a significant difference between two proportions. Therefore, the conclusion is the same. There is sufficient evidence to support our claim. And finally, conclusions about confidence intervals. If confidence interval limits include 0, then there is no between two population proportions. Basically, that means that the difference between P1